Today we're going to be proving some very, very cool properties of the exponential function for complex inputs. The function e to the z, which we defined earlier by means of the familiar power series that works for real numbers. So at this point you should be trusting that that is a function, that it defines an output, that it converges for every possible z in the complex plane because we proved that. And you should believe the Euler formula, e to the I z equals cos z plus I sine z. However, you should also have a nagging suspicion that perhaps this isn't the exponential function that you're familiar with, because if you've seen other definitions of the exponential function, maybe this definition is not compatible with the one that you have. And so as we move forward, we want to continue to entertain this doubt that, maybe this is the exponential function, maybe this isn't the exponential function, maybe I shouldn't really be calling it e to the z. And we'll get to the significance of those doubts a little bit later. So right now we're going to prove some properties of the exponential function. Some of them are basic, some of them are a little bit more advanced. So here are the properties. We're going to prove that e to the 0 is 1. That's true for the real exponential function as well. We're going to prove that its derivative is equal to itself. We're going to prove this sum law, which is familiar from the real case, and this corresponding difference law. We're going to prove a power law for it, and we're going to prove this peculiar property. It says e to the z plus 2 pi I is e to the z. That's for any z at all. If you add 2 pi I to the input, you don't change the output. So let's get started on this. A is completely trivial. And so I'm just going to say trivial. All you have to do is plug in 0 here. All the terms go away except the first term, which is clearly equal to 1. So B is almost as easy as that. To do B, we just have to differentiate term by term. Now, we've already established that differentiation term by term is a valid way to calculate the derivative of a power series. And so when we do that here, we get the derivative of this thing. The derivative of 1 is 0, so the derivative is calculated to be, the derivative of 1 is 0, the derivative of z is 1, the derivative of z squared over 2 factorial is z, the derivative of z cubed over 3 factorial is 3z squared over 3 factorial. The 3's cancel, and that leaves us z squared over 2 factorial. The derivative of z to the 4th over 4 factorial is 4z cubed over 4 factorial. The 4's cancel, and that leaves z cubed over 3 factorial. And we continue this way, and that, of course, is e to the z. So e to the z, as defined by this formula, is equal to its own derivative. And that already should be pretty impressive. In the real case, there is only one function which is equal to 1 at the origin and is also equal to its own derivative, and that is the function e to the z. So already we have some pretty powerful evidence that we've got a major agreement between this function and what we're familiar with in the real case. Now, so these were pretty easy. This one, f, is also pretty easy, and so I'm going to deal with it next before we reach to the significant one here. F, I misspoke. F is easy as a consequence of C. So I shouldn't jump straight to F because I haven't proven C yet. So we've taken care of the really easy ones. Let's deal with the sum law next. The sum law is, well, it should be somewhat surprising because we haven't defined e to the z to actually be an exponential, right? This isn't actually teaching you how to take a complex number and literally raise it to the power of another complex number. It's just defining e to the z to be this crazy formula, and there's nothing really, there are no z's in the exponent here, which is kind of peculiar, right? So, so this law really does require checking and is a very significant law. It's, again, going to be more evidence that this is behaving like the real exponential function. So let's prove this. So this is kind of tricky. So we have e to the w plus z so this is the proof of C. E to the w plus z is going to be, well, there's only one thing I know about it, and that's this. Well, I suppose there's another one over here, but it's not useful for this. So I know that it is this power series. So this is the summation n equals 0 to infinity of 1 over n factorial, and then we get a w plus z to the n. And honestly, there's only one thing we could possibly do with w plus z to the n, and that is we could use the binomial formula. And so let me remind you of the binomial formula. The binomial formula tells us that the summation of, let's write x plus y to the n, I'm sorry, I wrote it wrong. It tells us that x plus y to the n is equal to the summation from I equals 0 to n of x to the I, y to the n minus I, and then it tells us what coefficient to put here, and that should be n choose I. And n choose I, of course, n choose I is n factorial over I factorial n minus I factorial. So that's the binomial formula. And it works for real inputs, it works for complex inputs. In fact, it works in any commutative ring. So we can trust that the binomial formula is true for this summation w plus z. So let's throw it in there. So we get the summation n equals 0 to infinity of 1 over n factorial times a further summation, summation I equals 0 to n of the n choose I. Now I'm immediately going to substitute this factorial formula for n choose I. So I get n factorial over I factorial n minus I factorial, and then w to the I and z to the n minus I. So there we've applied the binomial formula to open up this summation w plus z to the n into this formula. Now that's a mess. I would like to pull this out here and start canceling the n factorial. I can't pull this out because it depends upon I, but I can push the n factorial in. And if I push the n factorial in, then it will cancel this n factorial. So let's do that next. This is the summation n equals 0 to infinity of the summation I equals 0 to n of, now push this in and cancel it, 1 over I factorial times 1 over n minus I factorial times w to the I times z to the n minus I. And now notice that we've got n minus I, I. Let's combine those. So let's just rearrange slightly so that it's a little bit more obvious what's happening. This is the summation I equals 0 to n of w to the I over I factorial times z to the n minus I over n minus I factorial. And now it may feel like we're really in the woods here and there's a lot left to do, but in fact we're done. It doesn't look like it, but we're done. So this, remember, is a formula of the form I equals 0 to n of ai b n minus I for two series A and B. So what do we have here? This is the Cn from the product formula. And that's why we have a whole 42-minute video that basically does nothing but establish that product formula for two power series. Well, that's one of the reasons. So that Cn from the product formula takes this form. If you want to take the product of two power series, then that formula tells you how to do that. The coefficient of the nth term of the product of two power series is going to be this thing, which is sometimes called a convolution. It's going to be a sum I equals 0 to n of these two terms, ai, bn minus I. What's the ai and what's the bn minus I? In this case, the ai is w to the I over I factorial, and the bi is z to the I over I factorial. The bn minus I is z to the n minus I over n minus I factorial. So this is exactly the formula that we want for the nth coefficient of the product of two series. And that means that this is nothing more than a formula for the product of the two series. And what are the two series? The first series is the series of the sum of powers of w over factorials. And the second series is the same, but powers of z over factorials. So the first series is nothing more than e to the w, and the second series is nothing more than e to the z by the product formula. So that was easier than expected. We just apply the definition, expand by the binomial formula, regroup, and use the power law. So, so there we have it. That's the formula for the sum, for the exponential applied to the sum w plus c. I want to remind you, this applies to real w and complex w alike. So we can plug in any values we like here. more evidence that the exponential function really is the exponential function, right? It's not just some crazy function I invented. If it's going to obey all of these properties, then I suppose it really is, behaving like the right function. Now, let's move on to part D. For part D, you can see that this method that I've illustrated for the sum law is probably not going to work. I mean, I could do this. I could do w minus z, and then I could expand by the binomial formula, and I get a minus 1 to the I, and then we could see what happens here. But it's probably not going to work, and primarily that's because I don't have a quotient formula for the nth coefficient of the ratio of two power series. So there's no way for me to close the deal here when I get to the computation. That's okay. D can be deduced from C without really any effort. So what we're going to do is we're going to erase the proof of C, and then we'll prove D on the basis of use of part C, now that we've proven it. So how do we prove D? We basically just apply C to the right values. So proof of D, so we apply C to e to the w. So e to the w, which is equal to e to the w minus z plus z. So in other words, I'm going to think of e to the w itself as a sum, like e to a sum. And the sum that it is w minus z and then z. So what does part C tell us about this summation? It tells us that e to the w minus z plus z, that is a sum of two things, namely w minus z and z, is equal to e to the w minus z times e to the z. So the first and the second. And then notice that this is just e to the w, and then we just divide both sides by e to the z. I hope I did that right. Yeah, so solve for this term here. So e to the w minus z is equal to e to the w, and then divide both sides by e to the z. E to the z, just as desired. So that establishes part D. So we've got check, 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 we're okay. And now part E. So part E is a power law. Now you might think I've given kind of an incomplete statement of the power law. You might expect a more general statement of the power law. And let me suggest an alternative to E. Before I prove E, let me suggest a more general statement of E. So let's call this a generalization that we might expect of E. And I'm going to put a question mark here. So you might expect me to say that e to the w times z is equal to e to the z to the w, or you might equally expect that that would be e to the w to the z. So you might expect this as a more general form. Here I'm saying e to the nz is e to the z to the n, but only for natural numbers n. And so you might be a little disappointed and you might expect a better statement. And these would be stronger and more interesting statements, more general, more useful. Yeah, they would. The reason this statement of E does not take this form is, as yet in the course, we don't have a definition for the right-hand side of these equations, right? We don't have a definition for this or this, which is effectively the same thing. Why not? Well, we have a definition of e to the z now. The only time we have complex exponentiation defined is when the base of the exponent is the special number e. Nothing about this work allows us to calculate I to the I, or even 2 to the I, right? Nothing about this work gives us a general form for any complex number raised to the any complex power, and we would need that to interpret this, right? E to the z, okay, e to the z is by definition this, so this part inside the parentheses is okay, we have a definition of it. But then that's going to give you some other crazy complex number. And to raise that to an arbitrary power w is basically arbitrary complex exponentiation. And we don't even have that defined yet. So I can't do that. Over here, though, we do. So here, if n is natural, then taking a complex number to to a non-negative integer power is just repeated multiplication. And so we can interpret this as the repeated multiplication of e to the z with itself n times, and then that this kind of thing is sensible for us to assert, whereas this is not yet sensible because it involves arbitrary complex exponentiation. So that's the reason why e is kind of special and it just forces n to be natural here. So that said, the proof of e is just totally trivial. E to the nz is equal to e to the z plus z plus z plus z, and how many z's are there? N, of course, which is e to the z, e to the z, e to the z, e to the z, by repeated application of c, which is e to the z to the n. And I mean, if you don't trust the dot dot dots, you could do an induction on n. So to give a completely formal proof, you would probably want to write this as an induction on n. And you would induct, of course, using part C in, well, in the base case you wouldn't need it, but in the induction step you would need to invoke part C. So, so part E is pretty straightforward either way. And now part F is pretty easy too, as long as we have already proven Euler's formula here, right? Remember that we already proved Euler's formula. So part F follows from C together with Euler's formula, and let me just, for the record, illustrate that now. So proof of F is basically just an application of C. So proof of F, all we're doing here is we're taking e to the z plus 2 pi I, and that's going to be e to the z plus e to the 2 pi I. No, not plus, not plus. E to the z times e to the 2 pi I. And then what is e to the 2 pi I? Well, Euler's formula tells us what e to the 2 pi I must be. It must be cosine of 2 pi plus I sine of 2 pi. And, well, both of these are trivial to calculate, right? Cosine of 2 pi is 1. Sine of 2 pi is 0. So this whole thing is 1. And we get e to the z times 1, which is e to the z. So this shows that e to the z, which is an exponential function, is also a periodic function. It's not periodic in the sense that when you shift the graph to the right and the left, it repeats. It's periodic in the sense that when you shift the graph to the imaginary direction 2 pi units, or in the negative imaginary direction 2 pi units, then the graph repeats in that direction. So that visualization, I mean, it's hard to visualize, but the periodicity is in the direction of 2 pi I. So the exponential function, so the way, one reasonable way to try to imagine this is we have the complex plane here, there's the real axis, and there's the imaginary axis. Then here you have a value, let's call this pi I, and then here you have a value minus pi I. And on this strip, e to the z is doing all kinds of interesting stuff. On the real part, it's being the real exponential function, and over here, it's doing interesting things on this strip. But it's periodic with period 2 pi I. So if you transport this up 2 pi units, then this whole strip will land here. And if you transport it down 2 pi units, it will land here. And then whatever e to the z is doing here, it's just a repeat of what it's doing here. So all the behavior of e to the z here is doing exactly the same thing again here, and exactly the same thing again 2 pi up, and exactly the same thing 2 pi down. So it has a lot of interesting behavior, but once you understand the behavior between minus pi and pi, or same way of thinking, once you understand the behavior between 0 and 2 pi, then you understand the behavior everywhere else by just transporting that data up and down. So these are some of the basic properties of the exponential function, and I hope that I've convinced you that it really is an exponential function. It really does obey all of the properties of the real exponential function.